All right, this is AP, AB, and BC Calculus. We are doing Unit 8, Section 9, which is volume with the disk method. So we're revolving around the x or y axis here. So let's go ahead and get started. So let's talk a little bit about what solids of revolution are, because I think that's going to sort of shape moving forward. So essentially, we can create solids by rotating a defined area about an axis of rotation, which I will frequently abbreviate AOR just for our sanity, right? So the region carved out creates a solid. So if the area of the region is something like a rectangle, we can actually just use basic geometry to find the volume. So here are two examples of how a cylinder is created by rotating a rectangular shape around an axis. So if you look at this first graph, right, we have a rectangle, this sort of like orangey rectangle, is rotated about the y-axis, and you can see that the shape that is carved out when you rotate that shape, what would be carved out is a cylinder, right? Similarly, if I had a rectangle that I rotated about the x-axis, right, you can see that the shape that would be carved out by that rectangle would be a cylinder. So as we've seen in previous sections, when the area is not some convenient geometric shape, we're going to need calculus to find this. So we could find the volume of these two cylinders using geometry because, again, the rectangle that we're using is a convenient geometric shape. That makes another convenient geometric shape, which in this case is a cylinder, and we could find the volume of that. But as we pick weirder shapes, it's going to be harder to do that. So let's go ahead and look forward at what happens when these are weird graphs. So here are some images of solids that we could create, but that would require calculus. So if I were to take this mound right here that I have, right, and I were to revolve this way, right, around the axis, or the other way around, like this arrow says this way, same idea, right? If I revolve this around the y-axis, what I'm going to get is this like weird kind of bundt cake shape. But you can see, and I got these images because I don't have the ability to draw these lovely see-through images. I got these from the interwebs, but you can see that that if you rotate this shape around, you'd get this 3D kind of like bundt cake shape, okay? Same idea, if you took this shape here and you rotated it around, around the x-axis, we'd get this kind of cup shaped thing, or maybe looks like a vase, right, that has a curve on the inside and also a curve on the outside and this big open space in the middle. And we're going to learn how to find these volumes using calculus in some of the videos moving forward. Maybe not these exact curves, but that's the idea. So let's talk about what the disk method is. So the disk method is sort of like looking at a stack of CDs, but all the CDs vary in size. So you can see that if I were looking at this stack of CDs, this is a cylinder, right? Like this is a cylinder shape from the outside. Each one of the CDs is a disk, right? And if I put a bunch of the disks together, then I don't just have area, I have volume, right? I find the area of one CD and I get volume if I add them up in a giant stack together. So if you find the area of one CD, meaning area is pi r squared, since the CDs, so we'd stack them up, right, and get volume. But since these CDs are going to vary in size in our problem, right, and if you look, you can go back here and see that so not all of the CDs that I'm going to have. So if I, well, that one doesn't quite work well. So I'll give you a better image in a sec. So not all of the CDs are going to be the same size, right? We're going to get different size shapes. Then we're going to have to write the area of a CD not as a constant like area equals pi times 5 squared, but as area equals pi times some function of x or y, right? And then we're going to use integration to sum up all the CDs, to add all the CDs, and that would give us volume. Just like here, we add up all the CDs to get the volume, right? If the CDs were all exactly the same size, you wouldn't need calc. You would just do the area times the height, which gives you volume, right? So that if the CDs were all the same size, we wouldn't be in calculus class. They're all going to be different size disks. So let's talk about the disk method. The area of a single disk is given, as you would expect if we go back to that CD, by pi r squared, because it's just a circle, right? So this is a circle with radius r, pi r squared is the area. Ignore the fact that this looks like an empty hole in the middle. We're going to assume it's a solid disk. The trick is that if our axis of rotation is horizontal, so if I'm rotating this way, right, if I'm rotating this way about the x-axis or any horizontal axis, so or y equals a number, then I'm going to need to write the radius in terms of x, right? So radius will be in terms of some x function. If my axis of rotation is vertical, like the y-axis or some equation that's x equals a number, right, a vertical line, then I'm going to need to have my area in terms of y, meaning my radius will be in terms of y. That's it. So, so basically, each disk is infinitely thin and has a width that is just dx or dy, depending on which axis you're using, right? So the volume of each infinitely slim disk is just ax times a of x times dx, or a of y dy, depending on which axis of rotation you're using. To add up all the disks, we just use integration from the first disk to the last disk. So let's go ahead and walk through how we do this. It's essentially the same concept as what we saw with cross sections that are defined, except the area is always going to use the formula pi r squared, and our job is to find r. So we saw that with other values, but that's the gist. So some steps that are really helpful. If you're given a graph, that's awesome. If you're not, make a really rough sketch. It doesn't need to be a beautiful picture, but it helps to have an idea of which function's on top of which thing or what this is going to look like. If you don't have a visual, you will tend to pick the wrong expression for r. Just knowing that from years and years of experience, literal decades of experience at teaching this, if you can't see it, you are more likely to pick the wrong r. Try to draw one disk somewhere in the middle of the shape, right? So draw it like it's coming out of the page, and I'll show you what I mean by that in a sec. And then we want to find the radius. We've seen this in previous videos, that if we have a line that's vertical, right? If our radius is a vertical line, we do top y minus bottom y. If our radius is a horizontal line, we would do right x minus left x. Once we write our equation in terms of x or y for the disk area, we go ahead and find our bounds and then set up our integral. Sometimes we'll be asked to integrate, oftentimes we will not. Sometimes we'll just be asked to set up. Notice sometimes we'll be asked to integrate by hand, sometimes we won't. So let's walk through one of these. The region bounded here, right, by this cube root of x, the x-axis, and the lines 1 and 8, right, x is 1 and x is 8, is rotated about the x-axis, so it's rotated this way. This is my axis of rotation, right, axis of rotation. To create a solid, find the volume of the solid that's created. Okay, so what's happening here is that this shape is rotated this way. So it's gonna kind of look like a little bit of a bullet shape, right, when we rotate it. I'm gonna pick a disk somewhere in the middle, okay? I'm gonna pick this and I'm gonna rotate and say, hey, there's my CD, right? So this is the thing I'm gonna call my disk. So once I draw that, I say, cool, so the radius seems to go from the axis of rotation up to the curve. Well, the curve is the cube root of x, and the axis of rotation seems to be where y is 0. So it seems to me that my radius is top curve minus bottom curve, or in this case is just the cube root of x. The area of one disk is pi r squared, so there's my r squared, or I could write this as pi x to the 2/3, right? That means that to find the volume, I'm going to start at the first CD and end at the last CD. So I'm going to integrate from 1 to 8 of pi x to the 2/3 dx. Now this is math I can do by hand, which is why it says this is non-calculator and verify on a calculator. I'm going to go ahead and yank the pi out in front and integrate from 1 to 8 of x to the 2/3 dx. So I up the power by 1. 1 more than 2/3 would be 5/3, right? Because that's 2/3 plus 3/3. So I'm going to get that this is a pi. Since it's an x to the 5/3, I'm going to need a 3/5 in front of this. And I'm evaluating from 1 to 8. So I get that this is a pi. And I might yank the 3/5 out. You could. It's a coefficient. So I might just go ahead and make this a 3 pi over 5. And then when I plug in 8 to the 5/3 minus 1 to the 5/3, I'm going to have a refresher about how 8 to the 5/3 works, because this is a thing you are expected to be able to do without a calculator. This is the cube root of 8 to the 5th, which means it's a 2 to the 5th or a 32. So I end up getting that my answer is that the volume, I have this 3 pi over 5, right? I get a 32 minus 1. So I end up getting 3 pi over 5 times 31. I'm pretty sure that's a 93 pi over 5, right? Now, the trick here is if you want to check it on your calculator, there are two options. You can either check it on your calculator, get a decimal that you can't math frac because of the pi, and then just type in 93 pi over 5 and see if it's the right answer. Or you could integrate the thing without the pi. You could integrate just this, see what you get, and then put a pi after it. That's usually the easiest option. So to check this on my calculator, I'm going to go ahead and do math 9, right? I'm going to pick that my function is the x to the 2/3. So let's do x caret 2/3, right, comma, with respect to x from 1 to 8. And what should happen is, since I'm checking this answer, I should get everything but the pi. So basically, I should get a 93 over 5. So if I math frac, there's my 93 over 5, and that checks out. It's the right answer. All right. So let's keep moving, right? So Another one you should be able to do by hand, and then we'll get into the ones that you're not going to do by hand because they're disgusting. So same idea, we have an x squared, we have line x equals 2 and the x-axis, right? We're rotating this way about the x-axis, so this is my axis of rotation, right? And what's going to happen is we're going to create a shape that, oh, that's a terrible drawing, hang on. We're going to take a shape, it's going to look kind of like this. I did a terrible job, but it's going to spin around this way and kind of look like a cone shape, okay? And again, I did a terrible job drawing it, but if we take one disc somewhere in the middle, it's going to look like this. Right, that's my one disc. And again, I did a terrible job drawing it, but that's okay. So my radius is going to be top minus bottom. So the radius is going to be the top curve, which is x squared, minus the bottom, which is 0. In this case, my radius is just x squared. The area of a disk is pi r squared, so that's going to be pi x squared squared, or pi x to the 4th. So my volume will be from the first disk to the last, which would be the integral from 0 to 2. I'm going to yank the pi out in front and just integrate x to the 4th. So I get, this is a pi, x to the 5th over 5 from 0 to 2. My volume should be a pi times 32 fifths minus 0. So I should get 32 fifths pi, or 32 pi over 5. Again, to check this in my calculator, I'm going to check this part without the pi. So I'm going to go ahead and hit second enter. And I'm just going to make this an x to the 4th. And we're integrating from 0 to 2, right? And I'm going to do that, and then I'm going to math frac, which that is a 32 fifths. So then I check that this piece is right, and I know that the pi is just sitting in front. So that checks out, and that's right. Cool. So let's keep moving. So I think now we're entering the uglier ones that we're going to use a calculator for in all likelihood. Okay, so the region bounded by the curve x equals y squared plus 1, the y-axis, and the lines from -1, y is -1 to 2, is rotated about the y-axis. So now this time we're rotating this way, right? So what's going to happen, and again, I'm terrible at drawing this, but basically, oh, it's terrible. Oh, that's really bad. Hold on. I can do better. So bad at this. Okay, so it's gonna rotate around this way, right? So it's gonna kind of look a little bit like a pedestal, right? So if I rotate this, here's one slice that's rotating around. That's one disk. I just pick a random disk in the middle, and I notice that my radius is a horizontal line. So my radius should be the right curve minus the left curve. Well, the right curve in this case is the y squared plus 1. The left curve is just the axis, so it's 0. And you'll notice that there is a trend here that right now we're rotating around x and y axes, which makes this a slightly easier problem. It gets more complicated when I start rotating around a different line. So I get this radius. I know the area of a disk is pi r squared because it's just a circle. So that's pi times this thing squared. Now here I did say, again, non-calculator, which is a little mean of me, but we'll manage. The volume is going to be the integral from the bottom y value to the top y value because we're integrating with respect to y. So there's going to be a pi in front. It's easier to yank the pi out in front of y squared plus 1 quantity squared with respect to y. So this is what you're going to need to set up. Now, if it's if it's calculator, you could just type and get an answer. Unfortunately, this one said non-calculator. So since it says non-calculator, we're going to walk through it once. If I FOIL this out, right, if I FOIL this guy out, I'm going to get that this is a y to the 4th plus 2y squared plus 1. So what I'm integrating is y to the 4th plus 2y squared plus 1 with respect to y from -1 to 2. So that's my volume, right? So this is just kind of separate work, right? This was work. It's not actually equivalent. It's just the inside. So I'm pretty sure that I get y to the 5th over 5 plus 2/3 y cubed plus y from -1 to 2. I'm just going to leave that pi chilling out in front. So I get 32 fifths plus 16/3 plus 2 minus -1/5 minus 2/3 minus 1. And then we're going to clean that up a little. Again, this is not an unreasonable ask for a non-calculator, but it's a little bit tedious. It's not horrible, but it's not nice either. So I'm going to get a plus 1/5, a plus 2/3, and a plus 1. So I'm going to suggest you combine stuff together that already has the same denominator. So I'm going to get 33 fifths, right? I'm going to get 18/3, which is nice. So 18/3, I can go ahead and make a 6, so that's cool. right? And I'm going to get a plus 3 here as well. So I'm going to get plus 3. So that's not awful because I only have to get a common denominator of 5 now. So I have a pi. This is a 33/5, and then this is a 9, so it would be a 45/5. So I'm pretty sure I get 78/5 with a pi. So that's what I get, and then we'll check on the calculator. Again, the smart way to check on the calculator is to do this piece on a calculator and then leave the pi next to it, right? So if I want to check it, what I'm going to do is I'm going to go ahead and do math 9, right? And I'm going to do x squared plus 1 whole quantity squared, comma, with respect to x from -1 to 2, right? And that's because without the pi, I can math frac it. So I'm going to math frac. I'm going to get 78/5, which is exactly what we have down here, right? That checks out. I got this piece, and I know that there's a pi after it, so that's fine. If you wanted to put this in your calculator and just get the actual like decimal answer, if this were a calculator section, you could either give your answer as this, right? You could have used the calculator to get this and math frac it, or you could type it in and get this, right? That would be the approximate answer. So this is exact, this is approximate, right? So either of those would be fine. And again, you may not have to do one like that by hand, but I just want you to be prepared that it's a possibility. Okay, so let's go ahead and try another one. So the line x equals cosine y, which is the curvy piece, the y-axis, and line y equals 0 is rotated about the y-axis to create a solid. So we're rotating this way, right? So basically we're going to get a disk that looks like this. That's my radius, right? And it's going to make a shape that kind of looks like a Hershey's Kiss a little bit, right? Like the 3D, it's going to look a little bit like a Hershey's Kiss. So the radius is going to be the right curve, which is cosine y, minus the left curve, which is x equals 0, so just cosine y. That means that my area is pi r squared, so that's pi cosine squared. My volume is going to be from the bottom y to the top y. Now, the trick here is that we actually don't have this bound, right? We're going to have to figure out what this bound is. So we can kind of figure out the bound because we're trying to figure out essentially when cosine of y equals 0. Well, cosine is 0 here and here, and if you look at this value, that's around a 1.5. That's definitely pi over 2. So in this situation, the angle is pi over 2. So we're going to be integrating from 0 to pi over 2 of a pi times cosine squared y dy, right? Now, this one's tricky as non-calculator. So this is actually tricky. I probably would let you do this one on a calculator, but I'm going to walk you through. So if you were doing this on a calculator, right, if you were doing this on a calculator, you'd put in, you can go ahead and get the answer by doing pi, clear, by doing pi, math 9, and then you'd have to do cosine of x whole quantity squared, right? Because that's how we square a cosine, is the whole cosine squared, right? Comma, with respect to x from 0 to pi over 2, right? Let's double check that that's right. The cosine is squared. Oh, and I didn't need the caret. I could have just done, I don't need the caret because I pressed the squared button, my bad. Okay, I meant to do caret 2 or squared, and then I did that. All right, so I hit enter, I get an answer. So I could get that this is 2.467, and that's great, okay? But the trick is, if you wanted to do this by hand, so this is actually tricky by hand. If you want to do this by hand, you have to use what's called a power reducing formula. So you have to use that cosine squared y is actually 1 plus cosine of 2y all over 2. So if you were going to do this by hand, this is a pretty tricky one. So in all likelihood, I would probably not actually make this a problem by hand. I would probably make this a calculator question. If you were going to do this by hand, you would have to, so I'm just going to do the work for a sec. You would have to rewrite this as a 1/2 plus 1/2 cosine 2y. You'd integrate and get that this is a 1/2 y, right? Plus, this is actually u sub because the u would be the 2y. So each time you differentiate, you multiply by 2. So when you integrate, you would divide by 2. So you're going to get that this is a 1/4 the sine of 2y, right? That's what this thing would integrate to. So if you were doing this by hand, right? So that's my work for what that would look like by hand. If I were doing this by hand, my volume would be a pi, and then 1/2 y plus 1/4 sine of 2y from 0 to pi over 2, and then I'd have to plug in and get the values. So if I did that, I'd get that this is a 1/2 pi, let's leave the pi out in front, my bad. pi in front, right? And I'd get that this is a 1/2 of pi over 2 plus a 0 because it'd be 1/4 sine of pi, which is gone, minus in parentheses 0 plus 0. So that's at least gone. So I would end up getting that this is a pi squared over 4, right? And if we type pi squared over 4 into our calculator, so pi squared over 4, there we have the right answer, right? So that's that same 2.467. So we did it right, okay? Again, that's not likely to be one that I would actually have you do by hand. So, okay, so this is definitely, I don't know that I would actually make this a non-calculator. This is tricky. It's tricky. We'll see if I'd actually make this non-calculator. Maybe I was a little aggressive when I made my slides. So the region bound by the curve g of x equals 1/8 x cubed, so that's this. The y-axis and the line y equals 1 is rotated about the y-axis. Yikes, that's why this is tricky, okay? So this is tricky because this was in terms of x, but I need it in terms of y. So I'm going to have to solve this thing for x. So I'm going to get that this is an 8y equals x cubed. I'm going to get that the cube root of 8y equals x. Or I could do cube root of 8 times cube root of y is x. So I get 2 cube root of y is x. The trick part of this problem is I need to rewrite this because look, if you're rotating this way, right? If you're rotating this way, you're going to need to have a radius. That was not very circular, my bad. You're going to have a radius that is right minus left. Well, in order to have right minus left, you need this curve in terms of y, not in terms of x. So your radius here is going to have to be 2 cube root of y minus 0, or just 2 cube root of y. That's the tricky part. The tricky part is that you have to solve this for the other variable. Now, there is another way to do this with what's called shells, but the AP actually removed that from their set of lessons. They don't actually teach shells anymore. There is another way to do this with shells that would not involve solving this for y. But because the AP doesn't teach it, their scoring guidelines actually don't even include it as an option. It's not mathematically wrong, but it makes the most sense to teach you what they're specifically teaching you. So again, we're not going to talk about shells in this course. I might do an additional video of it that you don't need to know just because it bothers me that you wouldn't know what that is. But okay, so once I know that that's the radius, right, I had to solve it in the other direction because I need right minus left, right? I'm going to say, cool, that means the area is pi. And this one you could do as a non-calculator. R squared, right? Which means that I'm going to get 4 pi, and then this is a y to the 2/3, right? That's what the cube root squared is. So my volume should be the integral from the bottom y to the top y. So I'm going to put the pi, I'll probably put the 4 pi in front in all honesty because I have this coefficient. Makes the most sense to put this in the front. So 4 pi, the integral from 0 to 1 of y to the 2/3 dy, right? So I get a 4 pi. This is going to end up being y to the 5/3. So I'm going to need to times by 3/5 rather to get rid of that 5/3, right? So I divide by 5/3, which is the same as timesing by 3/5. So I'm going to get, sorry, extending the page, that this is a 4 pi times 5/3 of 1 minus a big fat 0, right? So I'm pretty sure I get 20 pi over 3, right? And we can check that on the calculator by plugging this guy in. So if I go ahead and do 4 pi, oh, and actually I probably wouldn't, I probably would just leave the pi out, right? So I want to see if I get a 20/3. That's the easiest way to check this on a calculator, right? So I'm just gonna, I'm gonna do everything but the pi. So if I want to check this on a calculator, right, to check this, the easiest thing to do is integrate everybody but the pi, right? Like leave the 4, just don't have the pi. So math 9, right? I'm gonna go ahead and leave the 4, right? So 4, it's a y to the 2/3, but remember we are gonna call it x because we integrate with respect to x, comma, with respect to x from 0 to 1, right? And then hit enter, right? And I'm gonna math frac. I don't think it's actually gonna frac the way I want. So I'm just gonna check if it's a 20/3. Oh, hey, it's not a 20/3. What did I do that's crazy? 4/3 x to the 0 to 1. Did I do something crazy? Oh, hey, that's, hey, look at me being super horribly dyslexic. Sorry, everybody. Let's go back for a sec. Silly Hogan. This was a 3/5 here, and I made it a 5/3 there. Oops, my bad. It's a 12/5, which is definitely 2.4. My bad. Oops. and that checks out. 2.4 is 12/5, so that checks out. Sorry, my bad, silly brain. All right, it happens. So you're going to find that that kind of stuff is incredibly frustrating when it happens to you on an AP, because you will literally have things exactly right, and then you will flip a number, and it is so incredibly frustrating. So that should be a 3/5, not a 5/3. Sorry, my brain is tragic. So I get a 12/5 pi. All right, but hey, this is why we check on a calculator. All right, so this is another tricky one, okay? So we have this region, right? This is y equals the square root of x minus 1, and it's rotated about the y-axis, so you're going this way. That means that your disk is going to look like this. That means your radius has to be right minus left, right? Because it's horizontal, so it has to be the right x minus the left x, which means that you need to solve this for, this needs to solve for x, right? So I have y minus the square root of x minus 1. I need to square to solve for x, and then I need to add the 1. So I'm going to get y squared plus 1 is my x. This is what I have to use. So this curve is y squared plus 1. That means that I'm going to get y squared plus 1 minus 0. So my radius is just y squared plus 1, right? That means that the area of this thing is pi r squared. So that's pi y squared plus 1 quantity squared, right? I'm integrating from the starting y to the ending y, so that's from 0 to 2, right? So this is going to be, my volume is going to be pi times the integral from 0 to 2 of my radius squared. Now, if this is a calculator section, great, you're just going to bust it out right now. Honestly, the easiest thing to do is, if you want to get the full answer not as a decimal, just integrate without the pi, right? So we've seen that already, so we do math 9, right? Integrate without the pi, just don't forget that the pi's there. So it's going to be x squared plus 1 quantity squared, comma, with respect to x from 0 to 2, right? And then I math frac, right? So math frac, I get 206 over 15, and I have to remember the pi. So I'm going to get, I don't even have to approximate then. This is a 206 over 15 with a pi, or approximately, and you can fix this by just hitting times pi. So so one of the things I'll tell you is, on a calculator section where you, on a free response in the old school test, and we'll see what it looks like this year, because, we've been, possibly remote, you get a calculator for the free response questions, and then you lose your calculator, but you get to keep the questions. Sometimes people realize at the last minute that, like, after they've already stopped using the calculator, they realize, oops, I forgot to type the pi into the calculator. So they got the 206 over 15, or maybe they got the 13.7. So you could also say this was approximately 13.733 pi, right? That would be the same thing as this. Sometimes they realize they forgot to type the pi, so they got the answer 13.733, but they no longer have a calculator, so they can't do 13.733 times pi. So I've seen people literally say, oh, cool, I know what I did wrong, and then they go back and add the pi, because you can still edit those questions, you just can't revisit the calculator, like you can't use the calculator again. Now, we've already actually done this one by hand, or one very similar. If you had to do this by hand, right, so if you were going to do this by hand, you'd have to FOIL out y squared plus 1 times y squared plus 1. You'd get y to the 4th plus 2y squared plus 1. So when you integrate, your volume would be pi, and this would be y to the 5th over 5 plus 2/3 y cubed plus y, and you'd be plugging in 0 and 2, right? You only really need the 2, right? Because when you plug in the zeros, those are all going to get knocked out. So that doesn't always happen, but it does happen if you've got no constant term, right? This is going to end up being a 16/3, right? Because that's 8 times 2, and this is going to end up being a 2. Right, so my common denominator is definitely 15. I have a pi. This is going to be 96/15. This is going to be 80/15, right? Because I'm timesing by 5 over 5. And this is going to be 30/15. Sorry, that was an 80/15. So I end up getting 110 and also a 96. So that's a 206. So I get 206 pi over 15, which is the exact answer we got on the calculator. All right, so three more. Okay. So example 4, this time we're going to use a calculator for sure, okay? I didn't give you a picture this time, and that's intentional. So the region bounded by this ugly f of x, the x-axis, and the line x equals 2 is rotated about the x-axis. So you have a calculator, you might as well graph it, right? So, so I have a 3x squared e to the negative 2x minus a 1, right? So I'm going to go ahead and zoom 6 and see what this looks like. Okay, so the area that we're talking about is this area. So let's let's just draw kind of a rough version of what this looks like, right? This thing seems to do something like this, okay? We're talking about this curve, the x-axis, and the line where x equals 2. So this is the area that we're talking about, right? This is the area we're talking about. The trick is we don't actually know what this bound is, right? I don't know this bound. I know that this bound is definitely a 2, so I'm going to have to find that bound, right? So I'm going to go ahead and do second calc 0, because that's what that bound is going to be. I'm going to go over here, oh, too far, to the left, cross the axis, enter, enter. Okay, so I get that this bound, which I'm going to call A, is approximately negative 0.396464, but I'm calling it A. So I need to quit out and store this as A. And we've seen this before. I hit X, and then I stow alpha A. I'm going to need to use that. All right, so I'm going to call it A, and I need to label it as A for my problem, okay? I know the other bound is 2. So what's happening is this shape is rotated about the x-axis, right? So this shape right here is rotated this way. I did a terrible job of showing it, but my radius is here. My radius is top, which in this case is 0, minus bottom, which in this case is f of x. Because they called it f of x, I am allowed to call it f of x, and I should do so. There's no reason to write out that ugly function and risk being wrong, okay? So that means that the area of this thing is pi r squared, which is just going to be negative f of x quantity squared. Or if you want, since you're squaring it, you could just make this a pi times the f of x squared, right? Because the negative squared would still be negative, right? So the volume of this thing is going to be a pi times the integral from a to 2, which is why I had to find a, right, of the function quantity squared with respect to x. And then type, and I get an answer. So when I type it in, I'm going to go ahead and put a pi in front, right, math 9, and then I need to square what I called y1. So I'm going to go to vars, over to yvars, function y1, quantity squared, comma, with respect to x from a, oh, not a 7, comma 2, right, from a to 2. Now, notice I don't need parentheses around the y1 quantity squared because y1 is automatically the entire y1. If I were doing something like y1 minus y2 quantity squared, then I would need parentheses. And so I get that this is a 4.029 or 30, depending on if you round or truncate, right? So here's what you'd need to do. You'd need to find this point, you'd need to set this integrand up, and you'd need to give the answer, right? That's what we're looking for. This can be in your head. It's helpful to do it for me. I personally write it out. I also write it out for you. I guess maybe I don't write it out if I were just trying to bust through a problem real fast by myself. But I write this out because I find it helpful. But you definitely need to set up the integrand with the correct bounds, the correct constant, and then actually integrate. Oh, as a side note, remember that you don't round this to 3 places until the final answer. You cannot write negative 0.390 as your bound or negative 0.391. You have to either write all the digits or you have to list all the digits once and call it a letter A and then use A. But you have to, it doesn't have to be A, it has to be any letter that is not currently used in the problem, right? You can't reuse a letter being used in the problem. All right, cool. So let's do P4, which is the same concept, right? Different function. So again, you might as well get a good idea for what this looks like because it's a calculator section. So my G is x minus 2.1, close the parentheses, to the 4th, right? And then I'm going to go ahead and, I didn't mean to type, oh, it's because I was over typing, times, so e to the, in parentheses, negative 0.1x, right? Close the parentheses, plus an x squared. Oh, my bad, meant to do squared, minus a 3, right? So we're going to go ahead and graph it and see what we see. Okay, so now I've got this graph that kind of looks like this piece right here, right? And I want this weird thing, right? It's the area bounded by this curve and the x-axis, and that's literally it. So they have to be talking about this area right here, and we're rotating about the x-axis. So that means that I actually have to find both bounds in this problem. I need to find an A and I need to find a B because those are the bounds that we're rotating around. I'm then rotating about the x-axis, so I'm going to take this thing and go this way. So my radius is top minus bottom. My radius is 0, which is the x-axis, minus g of x, meaning the area of this one slice is pi r squared, which is pi negative g of x quantity squared, but because you're squaring it, you can just go ahead and say that it's g of x squared, right? So g of x quantity squared. the volume is going to be pi times the integral from the starting disk to the ending disk, so a to b, of this g of x squared. So I can write the integrand without even knowing what a and b are, but then I have to go back and find a and b, right? So I'm going to go ahead and find a and b by doing second calc 0. I always work left to right. You don't have to, but that's how I roll. So I'm going to find the left 0 first. Left 0, right? Okay, and I'm going to quit out and store that as a. So I'm going to quit out x. Oh, my bad. Quit out again, x, right? And I'm going to store that as alpha a, right? And I need to write it down one time. I need to say, okay, cool, a is approximately 0.843920316 dot, dot, dot. Okay, that's my a. And then I'm going to quit out again. I'm going to graph again, my bad. Second calc 0, right? So second calc 0, I go over here. I need to start below the axis. That's left bound in this case. Right bound, I cross the axis and hit enter. So my b is approximately 1.72736313, dot, dot, dot. But then I have to quit out and store that, right? So quit out, hit x, and then store as alpha b, right? And then I need to integrate, so I'm going to go ahead and do pi math 9, right? And I want to integrate the thing I called y1, so vars over to y vars y1, quantity squared, comma, with respect to x from alpha a to alpha b. And I hit enter. And I get that this is a 1.400, right? And you do need to list both zeros because it is not a terminating decimal. That's rounded. It's rounded to those zeros, so you need to list it. All right. Last one, challenge problem. So we've seen this before. We have this graph that consists of the two functions. We have a region H and a region K. The shaded region is rotated about the x-axis. Set up an expression involving one or more integrals that gives the volume, and then use your calculator to find it. So when we saw this problem before, the trick to this problem that we saw before was that there are two separate functions in two separate regions, right? And we can't ignore that there are two separate parts to this problem. So basically, we're going to do this as two pieces. We're going to take this shape and rotate it about the x-axis and find the radius, right? But we're also, after this line, we're going to do the same thing here, but it's a different shape. So the blue chunk, right, the radius for the blue chunk is the top curve minus the bottom curve, which is going to be the negative x squared plus 6x minus the 0, right? So the radius for the blue piece is going to be this thing. The area for the blue piece is pi times this thing, quantity squared, which we're going to use a calculator so we don't need to clean it up. That means the volume for the first chunk, the chunk where h is, right? So the volume where h is going to be pi times the integral from 0 to 3, right? So the disks that will happen in the h window, right, of this thing. But then for the red section, the section where k is, right, starting at 3, the radius for k is going to be the top curve minus the bottom curve. So my radius for k is just negative 3x plus 18. That means the area for the k section of the graph, right, the area for the k section of the graph is pi times this negative 3x plus 18 quantity squared, which means the volume for the k section of the graph is going to be pi times the integral from 3 to 6, right, because those disks start at 3 and end at 6, of this thing. So if you want the volume of the entire thing, right, so the answer to this, right, so the answer that I want for the volume for the whole thing is that it's two integrals. The volume of this whole thing is pi times the integral from 0 to 3 of negative x squared plus 6x quantity squared with respect to x, plus the red integral, which was pi times the integral from 3 to 6 of a negative 3x plus 18 quantity squared with respect to x. That's the answer without the calculator, right? And then what I'm going to do to put this on my calculator is I'm basically going to type it as two separate integrals, right? I'm going to go ahead and call them y1 and y2 because I think that makes my life easier. So I think that squaring things is a lot easier when they're already typed in as y1 and y2, so that's what I'm going to do. So even when it's something like a line, I think I just would rather type it once here. So I've got my y1 and y2, right? So I'm going to go ahead and do pi, right, pi, and then math 9. I want to function integrate. This was the thing I called y1, so I'm going to go to vars over to y vars function y1, quantity squared, with respect to x from 0 to 3, right, plus pi, and then math 9. And you could actually factor the pi out and put a set of parentheses so that all this stuff is the same. Vars over to y vars function y2 squared, comma, with respect to x from 3 to 6, right? So that's where I'm at. I'm going to hit enter, and I'm going to get that this volume is 661.619. Okay? All right, and that's it for this video.